We spoke about vectors and scalar quantities. We were able to differentiate between distance and displacement. We were able to talk about speed and calculating average speed. We were also able to calculate velocity, but what we didn't do is calculating acceleration and defining what acceleration is. So acceleration, where there is change in velocity, there is where there is change in velocity, there is acceleration. So that's practically the basic definition of what acceleration is. So this is where we ended last time, where we were able to calculate distance. We were able to calculate average speed, and I told you that the formula for average speed is always total distance over total time. And every time you're calculating displacement, you have to use the parallelogram law of addition of vectors, where you are using Pythagoras theorem. Do you remember that?
Yes.
So you have to revise this. So let's now talk about the concept of acceleration. So I told you that where there is change in velocity, there is acceleration. So acceleration, if we can do some form of dimensional analysis, oh, my graphics, the other way. If we can do some form of dimensional analysis, you're going to realize that acceleration, by the way, formulas
Tara, you are making noise.
that I would want you to know. I'm going to send them to you on WhatsApp. You have to memorize them. Although, yeah, you have to memorize them. I'll show you. Become this, all right. So acceleration is final velocity minus initial velocity over change in time. So this here, sometimes they can say delta V. So every time there is this delta here means change. So every time there's a change in velocity, there will be a change. Every time there's a change in velocity, there will always be acceleration. And you remember that acceleration will be a vector quantity. So the SI unit for velocity is meters per second divided by this time here, time in seconds. So if you use your concept of mathematics here, every time you are dividing something, it will be meter over second multiplied by 1 over second. When you are dividing, you exchange the denominator for the numerator. Therefore, the SI unit for acceleration will be meter times 1 meter, second times second, second squared. So every time, please, the SI unit for acceleration is meters per second squared. So you can say acceleration is meters
Tara.
per second squared. So you can also write it like this, by the way. So this notation here, meters per second squared, comes from mathematics, so math. I'll teach you vectors so that you can understand that if you have a negative index, you can make it a positive index by making it a fraction over 1 and vice versa. But anyway, for now, I just want you to know that the SI unit for acceleration is meters per second squared. If you can't write it like this, I prefer you actually write it like this. So make sure you write it as meters over second squared. Don't be fancy, because I haven't yet taught you indices yet. So this notation might be a little bit confusing, why you say to the power -2, but this one is more direct. So so like I said, remember acceleration will be a vector quantity because velocity is a vector quantity. And the direction of acceleration is the direction change in velocity. So it's about final velocity minus initial velocity over the time taken. So let's try to answer some questions here.
Tara.
All right. So here we are saying, which is very important, except from straight line where we can have speed and acceleration at the same time. So this is actually very, very important. These 3 points are extremely important. So what are the situations where we have an object accelerating? This can also come in an MCQ. So there is acceleration only when there is a change in velocity. This is extremely important. It can come in MCQs, and it also applies with your motion graphs where you see a straight line. A straight line means there is no velocity. So please, there is only acceleration if there's this delta, this final velocity minus initial velocity, this change in velocity. That's where there is acceleration only. If velocity is constant throughout, there is no acceleration. There's just constant motion. So if you see a graph which is like, it starts accelerating like that, and then you see a straight line will represent constant motion. Constant motion means zero acceleration. If velocity is increasing, it's there. So if velocity is increasing, the object needs to be accelerating because with every increase in velocity, like this graph here, this slope here, with every increase in velocity, there'll be acceleration. So this one we can say is correct. Then the final one comes down for in terms of retardation. So acceleration has a vector that's in opposite direction. So we call that a negative acceleration, which is called retardation. So the final answer we want is acceleration, we call it retardation. So this is the third point. If the velocity is decreasing, object negative acceleration or deceleration or retardation. So we've said three very important things here. The first thing is that every time you have got constant velocity,
Okay, twamimona.
every time you have constant velocity, for example, this region here, we are saying there's no acceleration. Every time you have an increasing slope, we say the object is accelerating. Every time you have a decreasing slope, we are saying the object is decelerating. So three scenarios: a constant line, constant speed, acceleration is zero. An increasing slope like this, we're saying there's a change in velocity, meaning there's acceleration. A decreasing slope like this means the object is decelerating. So these are the three scenarios that apply when we're talking about acceleration. No acceleration, acceleration zero, increasing speed, meaning increasing acceleration, decreasing speed means deceleration. All right, so we have a sample question here. Let's try to analyze it. So it says, does it require us to draw a motion graph? I think it might somehow to just help us understand this scenario. Anyway, question 4 says a car is uniformly retarded and brought to rest. So uniformly retarded and brought to rest from a speed of 10.0 meters per second in 15 seconds. So find its acceleration. So here we have an object. So we have to collect the data here. So we have an object is uniformly retarded and brought, so this is retardation. So we say acceleration is final velocity minus initial velocity over time. So acceleration, remember it's retardating. So meaning the final velocity will be zero here because of this point here. The car is brought to rest. So initially it was at a speed of 108 meters per second.
Station.
So let me read this question through again. So it says a car is uniformly retarded. So meaning this is how the graph looks like. Let me draw the slope like so. So here, the initial velocity before it started retarding was 108 meters per second, and the final time is 15 seconds. And the final velocity that it reached is 0 meters per second. So they're telling us to find this slope here, to find the retardation. So what are we going to use? We're going to use this formula, and we're going to say, by the way, you have to know this formula. We're going to say acceleration is final velocity minus initial velocity over time. Because this object was under retardation, its final velocity is 0 minus its initial velocity,
-8.
which is 108, over the change in time, the time that it was retarding, which is
15
15
seconds.
seconds. So meters per second, that is 15 seconds. So all we have to do, we're going to realize that our acceleration will be negative because it's retardation. So we're going to say 0 minus 108, it's minus 108. Then we'll say 108 divided by 15. We're going to get a negative 7.2 meters per second squared. It's negative here because it's retardation, so we're going to get the positive value. We won't write negative 7.2. The negative means it's moving in the opposite direction. Imagine when you are in a vehicle and the driver applies the brakes, you'll be undergoing retardation or deceleration. It's not that you're actually moving backwards, but there's a force of friction that's pulling you back. So the forces of friction are greater than the forces that are driving you forward. No wonder the acceleration is coming out negative, because the negative means it's in the opposite direction, but you're not going to write acceleration as negative this. The negative means it's in the opposite direction. So you just get the modulus and say acceleration is 7.2 meters per second squared in the opposite direction. So here you've added your magnitude and you've also added your direction. So let me just explain this question once more. We defined acceleration as this, where there is change in velocity, there is acceleration, and it's a vector quantity. It's final velocity minus initial velocity over time. Final velocity.
Nimwenzi mukirasi naye mutekanye.
The final velocity is 0 meters per second, and the initial velocity is 108 meters per second divided by the time. So the change in time, which is 15 seconds. So if we subtract this, we're going to get a negative answer. But it's negative. We're not saying the car is moving backwards. No. We're saying that there's a force that's pushing it backwards, the forces of friction. So the resultant force is in the opposite direction. I'm going to talk about resultant forces when we talk about dynamics. But right now, just say the acceleration, the answer quite all right is 7.2 meters per second. It's negative 7.2 meters per second, but we won't write this negative. We're just going to say 7.2 meters per second in the opposite direction because it's retardation. So let's try answering question 5. This other question where we sort of try to piece in the information. We get the information and then we try to see what's happening so that we can follow the question properly. So our next question, now you have to pay particular attention to this one. So we have a driver here. So the driver of a car brakes. The driver of a car brakes when the car is traveling at 30 meters per second. So here, our initial velocity, our V initial is 30 meters per second. The velocity of the car is reduced to 10 meters per second. So our final velocity is 10 meters per second at a t of 5 seconds, or at least this one is a direct substitution question. Then the question is saying, what is the average acceleration? Although this one is a little bit, oh yeah, no, this is a direct change question. So you just say acceleration is final velocity minus initial velocity over time. The final velocity that was reached was 10. Again, here we are saying the driver of a car brakes. So here we are taking into account of retardation again. So we have to say 10, the final velocity, which was 10 meters per second, minus the initial velocity before the driver hit the brake, which was 30, divided by a time of 5 seconds. So if we subtract this, we'll get minus 20 over 5, and we're going to get our acceleration as negative 4 meters per second squared. Again, since it's retardation, we're not going to say negative 4 meters per second squared. Our final answer, here's my pen. Our final answer should say acceleration is 4 meters per second squared in the opposite direction. So we are taking into account of the magnitude and also the direction. So you have to be able to understand this concept. If you are in a car and the driver applies the brake, the car isn't moving backwards, no, but the direction of the resultant force is in the opposite direction. So the car is going to finally gradually slow down until it reaches zero, until it stops. So you don't say minus 4 meters per second squared because you're not actually going in reverse, but the direction of the resultant force is in the opposite direction. So you say the acceleration or the deceleration is 4 meters per second squared in the opposite direction. So sometimes questions would come where you have to substitute. They are going to give you a value of velocity, and using that information, you sort of have to substitute to come up with a value for acceleration. So it's like you're working in reverse, or you've been given a certain amount of known values. You've been given a certain amount of known values, and they want you to find the unknown. So this is a type of question that's like number 6 here. So question number 6, we're saying we have a sports car here. It's we've been given the value of acceleration, so it's accelerating at 4 meters per second squared. And then you pause here, you tell yourself, where there is acceleration, there is change in velocity. And the time here that we've been given is 10 seconds. Then the question here says, a sports car accelerates from rest. So from rest, again, this is a very important concept here. And then we are saying calculate the final velocity. So what we are saying, draw a sort of mini speed time graph for you here so that you see this question properly. So from rest here, we are at 0 meters per second. That's the initial acceleration. That's the initial velocity, sorry. So this is the initial velocity. So it accelerates at an acceleration of 4 meters per second squared. So this slope here, this graph is acceleration at a time of 10 seconds. So the time interval here is 10 seconds. So the question is asking us to find the final velocity. So imagine this question like this. So now that we have all the unknowns, we're going to say acceleration is final velocity minus initial velocity over time. The acceleration is the slope. It's been given as 4. The final velocity is the one that we want to find. So Vf minus the initial velocity, it's 0. Because the question says a car accelerates from rest. From rest, we have 0 meters per second. So we're not going to write it because it's like saying subtract by 0. But what we do know is the time, which is 10 seconds. So over 10 over 1. So here it's easy. So all we have to do is we've formed an equation. There's a fraction on the left-hand side and there's a fraction on the right-hand side. We've made this whole number 4 into a fraction by saying over 1. Therefore, we can now cross multiply. If we cross multiply, our final velocity will be 40 meters per second. So these are the scenarios in which questions can come where they are trying to tell you to find acceleration. It's either they'll tell you to find acceleration directly, like what question 5 told us to do, where we just plugged in. It's either they are telling you to find the opposite of acceleration, which is retardation. Retardation, your answer is going to be a negative. But after you get that negative answer, you're going to write it in a positive way. Like we did, we said maybe 4 meters per second squared. Then we're going to tell the examiner that it's moving in the opposite direction. So we said 4 meters per second squared in the opposite direction. Or you're going to have questions like this where you've been given values like initial velocity, acceleration, and the change in time, and they want you to find an unknown. And for our question here, our unknown was the final velocity. So we're able to use this equation to actually find the final velocity. So this is how questions will be coming in terms of physics, direct questions rather. So let's now move on to motion graphs. Or let's look at one more question here. This is an MCQ type of question. So what must be changing when an object is accelerating? Is it the force acting on the body? Is it the mass of the body? Is it the speed of the body? Is it the velocity of the body? This question is coming. So what must be changing when an object is accelerating? Every time an object is accelerating, there is changing velocity. There's that delta. No wonder acceleration is the rate of change of velocity with time. Acceleration is final velocity minus initial velocity divided by the time. So this is a very important concept. So let's try to look at an analysis of motion graphs. We're going to start with a speed time graph where we do not have acceleration. Then we're going to we're going to start with the distance time graph where we just have speed, no change in velocity, and no acceleration. Then we're going to move on to the speed time graph. The speed time graph is the one that the examiner wants you to know because it's the one that always comes year in, year out. It not only comes in physics, you're also going to find it in mathematics paper 1. Mathematics paper 1, there's nothing like choosing. You answer all questions and everything will be there. So that's the danger with mathematics. Math also has some physics, and they'll always bring a speed time graph. So I won't waste much of your time. You have to understand the distance time graph for MCQs, but the speed time graph, you have to understand it for section B, paper 2, for both physics and also mathematics. So we have to recognize just from the shape of both the speed time graph and the velocity time graph, in terms of the slope, what's happening, these are just straight lines. So if you can interpret a straight line, it's easy to interpret straight lines. So is the object at rest? Is it moving with uniform speed? Is it moving with uniform acceleration? Or is it moving with non-uniform velocity? Although they won't bring non-uniform velocity because it's A-level physics. You don't know that much of calculus in high school. Of course, you are required to know how to differentiate only. You are not taught integration as such, but non-uniform acceleration, these are now slopes, it's calculus. So we're going to end with uniform acceleration. So let's start our discussion with a distance time graph, which just shows a change in speed. The whole speed is equal to distance over time. This is the graph that we're talking about. There's no velocity, there is no acceleration. So to start off with, when you have a distance time graph here, you have got certain scenarios. You can see, like I said, the speed time graph is speed is equal to distance over time. So your x-axis will be your distance and your y-axis, your y-axis will be your distance and your x-axis will be your time. So every time you see a straight line, it means there is no motion. The object is at rest. For a distance time graph, a straight line like this means there is no motion. Please, this only applies to a distance time graph. There's someone on the door. Let me just pause. All right, so let's continue. So a straight line under a distance time graph, it means we have no motion. What of an increasing straight line here? So when we have an increasing straight line here, it means we have uniform speed. So we have uniform speed. So remember, like I said something important for motion in a straight line, for motion in a straight line, there is no difference between speed and velocity. So here when they say uniform speed, we're just saying uniform velocity. We're also saying uniform speed. So we started off with a straight line which said no motion. Then a slope like that which says increasing or uniform speed or velocity. Then we can have a line like that which shows increasing speed. So we can have, if I can complete a graph. So we started with a straight line like that, which means the object is at rest. This is increasing speed, uniform speed. Then this is increasing speed. These graphs and that's decreasing speed. So these graphs, they are usually for your MCQs. They are usually for your MCQs. When it comes to actual calculating of questions, they are going to bring speed time graphs. So in summary, on a distance time graph, if you see a straight line like that, no speed, remember, if you see distance in your y-axis and speed on your x-axis, that's a distance time graph. So a straight line, no motion, a line like that, uniform speed, a slope like that, increasing speed, a declining slope like that, that's decreasing speed. So reading the distance time graph, this is what I was explaining here. I've explained everything on this line. All right, so this is where the examiners wants you to know the speed time graph. So every time you see your y-axis, so your y-axis is going to have a velocity, and your x-axis is going to have time. So every time you see velocity with time, that's known as a speed time graph. A speed time graph is going to have changing speed or changing velocity. So where there is changing speed or changing velocity, there will be acceleration. So for this graph, you have to know what all these lines mean. In summary, you're going to see a straight line like this. A straight line, let me start with this straight line. Every time you see a straight line, it's going to mean the car is moving at a constant speed. Every time you see a slope like that, it's going to mean the car is accelerating. Every time you see a decline in slope like that, it means the car is decelerating. And for non-uniform, you're going to see some form of curves. These curves won't come at your level. Why is this graph significant? Because, like I said, there is acceleration. Under this graph, you can find acceleration. And again, they want you to use the area under the graph represents the displacement or the total distance traveled. And you're going to have a variety of shapes. If I cut this, there are three shapes that you can have under this graph for finding distance. And there are three formulas that I want you to know. Just one graph can have three formulas for area. The first one will be area of a right angle triangle, which is half base times height. The second one will be area of a rectangle, which is length times breadth. And the third formula, if you really want to be fast, will be area of a trapezium, which will be area is equal to half the shorter side, which is this side, you can call it A, plus close the longer side, you can call it B, the distance from there to there, multiplied by height. So these are the three formulas that you have to know to calculate distance or displacement under the speed time graph, which is represented by the area under the distance time graph. So area is equals to half base times height, area is equals to length times breadth, and area is equal to half a plus b close brackets height. So reading the distance time graph, I'm going to explain all this information, but you can write this in your notes and follow the video. So we're going to start off with a straight, we're going to start off with what's happening here. All right, a straight slope. A straight slope like that, starting at the zero axis like there. So this line here is parallel to the x-axis. So a line that's parallel to the x-axis, it means the car is at rest. You've seen this is the x-axis there, and it's right. It's actually not parallel, it's directly on the x-axis. So if you see the graph where the line is directly on the x-axis, it means the object is at rest in the speed time graph. So here, object is at rest, no motion, zero velocity, zero acceleration. But if you see that there is some form of change, you see here, this is initial velocity, and this is final velocity. So here there is a change, but the line is still a straight line there. Oh, now this is parallel to the x-axis. So this is parallel to the x-axis, parallel to x-axis. And then this one, like I said, it's actually on the x-axis. So if you see a line on the x-axis, zero, no velocity, the car is at rest. But here there is some form of change here. There's a value here, there's a final velocity and there's an initial velocity, and we have got a line here that is parallel to the x-axis. If you see a line that is parallel to the x-axis, there is uniform velocity. There's this uniform velocity, please. So a line that's on the x-axis, that's zero motion. A line that is parallel to the x-axis, it means there is uniform velocity. Then this line here, it's a slope. So we started off with a straight line where there is no motion, then a straight line like that, that's parallel to the x-axis, and now there is a slope there. We've made a slope. So this slope that has been created, there is final velocity there, and there is initial velocity there, and there is change in time there. There's a change in t. So final velocity minus initial velocity over time, that explains acceleration. So if you see a slope, it means there is uniform acceleration. If you see a decrease in slope, again here we have got uh, initial velocity, here we have got final velocity, and we have got change in time there. This is retardation or deceleration. So if you see a slope in the opposite direction, that's deceleration. So to piece it all together, in a nutshell summary, you are going to create a graph that usually looks like this when it's a speed time graph. They are going to say velocity. It's either you are going to make this graph on your own or they'll draw it for you. So velocity, and this is time. The object will start at rest. There will be a line that's parallel to the x-axis, meaning it's at 0. Then it's going to accelerate. Then it can move at uniform speed. Then it can decelerate. You have to know how to explain this because questions are going to come at time t is equals to 15 seconds, between t 20 and 15 seconds, describe the motion of the car based on the graph. So based on these lines that you are seeing, you can tell them either it's moving at a uniform speed within this line, you can tell them whether it's accelerating within this slope, or you can tell them whether it's decelerating within this slope. You have to know this. Okay, so this won't come because this is a non-uniform acceleration. It's called instantaneous velocity. So here we use calculus to calculate instantaneous velocity. This is A-level physics. So you just have to worry about this notation here and those formulas for area. So don't worry about this. Don't worry about this. It's a slope again. All right, so I'm going to solve one question for you because the rest of these are questions. So we're going to, when we meet next time, I want to see some form of answers. So you should, anyway, it doesn't really matter. As long as we solve this question properly. Yeah, let's solve this question properly. If we solve this question properly, you won't fail a time graph, either in physics or math. So you can just go back to the video and just rewatch it, watch the basic concepts. You won't fail a graph just by knowing this. So let's begin. Because I don't know, most students, when they see such a question where they say, draw a velocity time graph, the students just freeze. It's like their ruler and pen, they don't even want to move their ruler and pen. They're just scared. There's nothing to be afraid of. They are just straight lines. Can you be afraid of straight lines?
Yes.
They are just straight lines and just concepts. So if there's a line that's directly on the x-axis, the car is at rest. If there's a slope, it's accelerating. If there's a line that's parallel to the x-axis, there's uniform speed. If it's moving downwards in the opposite direction, it means it's decelerating. Then you just say area is half base times height, or area is length times breadth, or area is half a plus b, close brackets, multiplied by height. That's all. You even get all your, this usually carries about 10 marks to 15 marks, if I'm not mistaken, because you are given about 3 marks for drawing a correct speed time graph. So let's try to analyze this question. We have got a cyclist. So a cyclist started from rest. So when we are saying started from rest, they are saying you have to draw a line that is parallel to the x-axis. So from rest, we're drawing this x-axis there. So that's t. So at rest. So you've seen from rest, we're drawing this line that's parallel to the x-axis. We're already making marks. Then they are saying, and of course there will be a velocity here, a line for velocity. Anyway, let me draw it more professional. Let's draw some proper lines. So I'm going to start off with this line here from rest, like so. Then we're also going to put another line there. Did I just rub? Let me use freestyle. But you use a ruler when you're answering your question. So we're saying the cyclist is starting from rest. So that's the x-axis, and there'll definitely be a y-axis. For velocity in meters per second, you have to write units and time in seconds. So this cyclist started from rest. So that's the line here that we've drawn parallel to the x-axis. Then the question continues to say, achieved a speed of 10 meters per second squared, or 10 meters per second in 5 seconds. So there is a t. So I'm going to say t here is 5 seconds, and the velocity that he achieved was at 10 meters per second squared, meaning he was accelerating here like so. How do I know that this person was accelerating? Because he started from rest, then achieved a speed. So there was a final velocity, 10 meters per second squared, minus an initial velocity, 0 meters per second squared, over time of 5 seconds. So for now, this is how the graph looks like. Then they say he then cycled at speed constantly. So there's a constant speed. How do we draw constant speed? A straight line parallel to this x-axis. So a constant speed for the next 15 seconds. So for the next 15 seconds. So for the next 15 seconds, we have to, so for the next 15 seconds, so this is 15 plus 5. So for the next 15 seconds, so 15 plus 5, this will be 20 here. Yes, because if we subtract 20 from 5, so this constant speed here was in 15 seconds. So for the next 15 seconds, then they are saying finally he decelerates to complete his 30-second journey. So the final time he was decelerating, so deceleration, we're going downwards like that. So he's decelerating, and the T final there is 30 seconds. Please answer this question and draw the graph properly. So he started from 0. He gained a final velocity of 10 meters per second. He moved at a constant speed in the next 15 seconds. So we're adding 15 plus 5 to get this T here of 20. Then he decelerates. Sketch a velocity time graph for the whole journey. So we've sketched. Then now the question says, calculate his deceleration in the last 10 seconds of his journey. So we have to calculate his deceleration. So deceleration is this part here, right? That's the deceleration that we're trying to calculate. So again, we're going to say acceleration is final velocity minus initial velocity over time. So we know that the final velocity that you attain will be 0 because the car is going to stop. So 0 there, he was applying the brakes, 0, minus the initial velocity was this straight line here. So before he started decelerating, his initial velocity is 10 meters per second. So that's 10 over 30 minus 20. Now you see there is 10 seconds there. So in the last 10 seconds, so that's 10. So this would be minus 10 over 10. That would be -1 meters per second squared. After showing the examiner that it's -1 meters per second squared, we're going to say 1 meters per second squared in the opposite direction. In the opposite direction. We're telling them that retardation is, it's not like you're going in reverse, but we're telling them there's a resultant force that's pushing you backwards. More to be explained when we look at Newton's laws and dynamics. Now the question goes further to say, calculate the distance that he traveled during the journey. So the area under the graph. So here we're going to use area under graph. So area under graph. And how are we going to use that? There's this shape that has been made here called a trapezium. We won't waste time. You have to use the formula for a trapezium. We can't say triangle, rectangle, and triangle and add everything. That would be wasting time in the exam. We'll use the formula for area of the trapezium, which you have to know. So area under the graph will represent the distance traveled. So how do we do that? The area of the trapezium is very simple. So you're going to say area is equal to half, open brackets, the short side represented by A, add it with the longer side represented by B, close brackets multiplied by the height. The short side, you can see it, it's the distance from there to there. And the distance from there to there is 20 minus 5, right? Which is 15. So that is A. The longer side is from 0 there all the way to 30, which is 30, right? So B, the longer side is 30. The height of the trapezium is this length here. And that length is what? 10. So you have everything. So you just say area is half, open brackets, the short side 15, plus the longer side 30, multiplied by height, which is 10, this height here, which is 10. So you even get your calculator like, oh, I know this. You just say 15 plus 30, which is 45, multiplied by 10. Then you divide it by 2. Then you're going to get your area as 225. Therefore, the distance was 225 meters. So this is how you do it. I'm going to answer the physics past papers, and I'm going to explain more of these concepts. But please, this topic is like 30% of your exam, including math. Math, it's like 20, math, it's 10 to 12% of your mathematics exam also. So please, you have to revise this topic very much. Immediately, let me send this video. I have some work to do, so I'm going to send the video at 17 hours, exactly, 17:30, somewhere there. So I'll meet you tomorrow. Please study and have a good day. Let me just finish up some work. I'll see you tomorrow.